So let's look at some examples of vertical asymptotes. H of x equals 1 over x. We've already looked at this graph, and we know that this graph looks like this. And notice when as x approaches 0, it's negative, but very, very small. So 1 over something very, very small is very big, but negative, so I'm going to go down to negative infinity. And then likewise, as x approaches 0 from the right, I'm going to come up. I've done the same graph before. We've seen this. This gives me a vertical asymptote. And you notice that if I think of this as simply being f of x, oops, that's an x, and this as being g of x, that g of x is 0 at 0, but it is non-zero on this interval about 0. So that meets our definition. Now, another way that I think about this is, well, wait, I talk about that in the next example. It's probably a little bit better. Okay, here's another one, x minus 2 squared. This graph, I can see when x equals 2, I'll have 0 in the denominator. Each side of 2, it's defined. So it's going to be defined on some open interval about 2. It's always positive. This is going to give me a vertical asymptote. And because it's always positive, I know it's going to look just like this. Okay. I lied to you. I said I was going to talk about it here, but really I think I'm going to do 2 more examples. And in the 4th example I got lined up, then I'm going to point something else to you that hopefully make a lot of sense. Okay, so next one, sine x, cosine x. All right, cosine x equals 0 for x equals pi over 2, 3 pi over 2, 5 pi over 2, and so forth. There's a pattern here that I just established. So I can write this as x being equal to 2m plus 1 pi over 2 for n being 0, 1, 2, and so forth. Because see, when n is 0, I get pi over 2. When n is 1, 2 times 1 is 2, plus 1 is 3, just 3 pi over 2. When n is 2, 2 times 2 is 4, plus 1 is 5 pi over 2. If you haven't seen this before, a 2n plus 1 always guarantees you're going to have an odd number when n is an integer. Okay, so when x is 2n plus 1 over 2 times pi, cosine is going to be 0. Sine of x equals plus or minus 1 for x equal to this. So when cosine is 0, sine is 1. So every place that the denominator here, g of x, is equal to 0, the numerator, f of x, will be equal to 1. This is going to give me a vertical asymptote for every 2n plus 1 pi over 2. So let's go ahead and maple here, and let's just create a quick plot. The plot is going to be sine of x divided by cosine of x. And x will go from, let's go from 0 to, how about 4 pi? And then y equals, let's do just negative 10 to 10. Let's see what we get there. Now let's go ahead and change this thickness again because it'll be easier for you to see. And I'm going to make this bigger. There. Now hopefully it's nice and easy to see. Now remember I said before that when you see these vertical lines here, it doesn't really exist. It's just maple trying to connect the dots is all that really is. So if I wanted to add that discount equals true, now I'm going to have what the graph really looks like. But without it, the nice part about it, even though those vertical lines don't exist, They are kind of nice because it suggests to me where my vertical asymptotes are. And sure enough, each one of these is going to be a vertical asymptote. This is going to be pi over 2. This is going to be 3 pi over 2, 5 pi over 2, and so forth on to whenever I decide to stop. If I just make this a little bit bigger, go to 6 pi, it's going to be the same thing. It just simply goes out farther. Okay, this last one now is just a tad bit more challenging. I have x squared minus 4 over x cubed plus 2x squared plus x plus 2. First thing I want to do is, if there's going to be a vertical asymptote, it's going to be when the denominator is 0. So I really need to do is I need to factor x cubed plus 2x squared plus x plus 2. First thing I see is I'm going to factor on x squared from here, and I'll get x squared times what's left, x plus 2, plus my x plus 2 that's sitting right here. So now if I factor out the x plus 2, I will have x plus 2 times x squared plus 1. So this is the difference of squares, so I can factor that immediately. So I know right away that this is going to be equal to x minus 2 times x plus 2 divided by x plus 2 times x squared plus 1. Now notice that if I set this equal to 0, this is my denominator, this is going to tell me where my vertical asymptotes are. Well, kind of. This can only be 0 for x equals negative 2, because x squared plus 1 is never 0. I have two positive numbers added together. I can't get 0. So when x equals negative 2, it's a candidate for a vertical asymptote. But if you notice, x plus 2 is a factor of both the numerator and the denominator. So that's going to cancel out. So this is actually equal to x minus 2 over x squared plus 1 for x not equal to negative 2. See, this is defined everywhere. So this is actually equal to this everywhere except when x equals negative 2. Because when x equals negative 2, if I put negative 2 in here, I'll actually get a 0 over 0, which is, I believe I've alluded to earlier, it's the indeterminate form. So what I was getting at a little bit earlier is that if I have a situation where I have a value of x that gives me 0 in the denominator and the numerator is non-zero, now we're talking about a vertical asymptote. But see here, the only candidate for a vertical asymptote was x equals negative 2. But x equals negative 2 made this factor 0, but this factor canceled out. So this graph of this looks exactly like this, except when x equals negative 2. So in other words, what I have here is actually a hole. When x equals negative 2, there's actually a hole. Let's take a look at Maple real quick. Okay, so let's go ahead and plot. I need parentheses around my numerator here so that, Maple understands that this whole thing is my numerator. Divided by x cubed plus 2x squared plus x plus 2. Let's make x go from negative 10 to 10, y equals negative 10 to 10. Don't know if that'd be enough or not, but it's a good place to start. And let's go ahead and do thickness equals, let's take a look at thickness equals 2 this time. Not quite as thick, but maybe, okay, all right. So there we go. This is what my graph looks like. Okay, clearly y equals negative 10 to 10 is this too much. So I want a better picture of this. I'm going to change these to 5s. That gives me a little bit better picture. And make it bigger. Okay, when x equals negative 2, which is right here, there's a hole here, but you can't see it. There are no vertical asymptotes. There is, in fact, a hole here. Let's do this real quick. I'm going to modify this, and I'm going to draw this graph and x minus 2 over x squared plus 1, which we said were equivalent. And let's just see what that looks like. Okay, there it is. I just put this one in and graphed it. And what happened is it's the exact same thing. The red ones show up, and then the green ones show up. But so fast, it's instantaneous, you can't even tell. The difference is this is defined when x equals 2. I'm sorry, negative 2. And I can actually find this value down here by putting in negative 2 here. and that will give me the coordinates of my whole. Of course, negative 2 in this function is going to give me 0 over 0 in determinate form. All right, back to the idea of vertical asymptotes. This has, the original function has a value that makes the denominator 0, but it also made the numerator 0. That means that factor would cancel out, so there is no vertical asymptotes. If there were multiple values of x that made the denominator 0, and some of those canceled out, any that are still left over would result in a vertical asymptote.